Hi there everyone, welcome back to the channel. I'm the GCSE science teacher. In today's video, we're going to be learning about satellites and orbital motion for GCSE Physics. If you guys find this video helpful and you enjoy this sort of thing, give the video a thumbs up, share this with someone, and please do subscribe if you haven't already. Thank you so much for your support already, and I hope you guys find this helpful. So let's talk about it. Let's talk about the Milky Way Galaxy. This is where we are located. Our solar system is found within the Milky Way Galaxy. There are billions and billions of stars, amongst other things there. We've got our sun, which is the star in the center of our solar system. We have the 8 planets, which you can see at the bottom there. We've got dwarf planets as well. We've got satellites, artificial and obviously natural, such as the moon and some of the satellites that you might have heard of with like weather forecasting and Google Maps and that kind of thing. And we're going to talk about all of these components and how they actually orbit today. Like, how do they stay in motion? Because essentially, we are moving right now in space, which sounds amazing and crazy, but that is what's happening. We are on Earth and we are literally orbiting and moving around the sun. And around us is the moon. The moon is orbiting us as we rotate. That is our closest natural satellite. But we also have other satellites out there. We have satellites, like I said, that's used for weather forecasting and um, you know, discovery of the universe. So how do all these things stay in place? How do they not fall down and crash down in Earth? How do they not escape and wander off into space? These are all questions that we are going to answer today. Gravity, as we know, is the force that keeps the planets and the satellites, whether they're artificial or natural, in this circular orbit around the sun. And depending on the size of the object will depend on the attractive forces. So the smaller objects will actually be the ones that are attracted to the larger objects. And this is due to the mass of that object. So if you think about force equals ma, force is F, M is mass, and A is acceleration. That's Newton's law, essentially, of force, mass, and acceleration. This links to that topic, so I'll link that video for you if you're interested in Newton's laws of motion. We also know that as an object moves around in a circle, it actually exerts this force called centripetal force. So, constant and circular objects need satellites to travel at the right speed. And for circular objects, the force of gravity can lead to the changing velocity but an unchanged speed. This is due to velocity being a vector quantity, meaning that it has magnitude and direction. But speed itself is actually a scalar quantity, so it only has magnitude. Now, this causes velocity to change because of the changing direction which occurs all the time. You can see in this diagram here, the moon is orbiting the Earth and it's moving constantly around it, but it's changing direction. And because of that change in direction, it also causes there to be velocity there as opposed to just speed itself. So we can have an increase in velocity, but the constant speed, because essentially what's happening is you're changing that direction all the time. Velocity, which is changing, causes acceleration to occur. And remember, this is all due to the force of gravity, but there is also that force that I discussed a moment ago called centripetal force. And you can see that represented by the dotted white arrow. The centripetal force is actually acting towards the center of the object that is being orbited around. So you can see the moon is essentially orbiting around the Earth, and the centripetal force is acting towards the center. This is why, if you've ever, this is quite a random analogy, but if you've ever got a bucket of water and you've lifted it and spun it around a few times, the water stays inside the bucket even when it reaches the top of that circle if you spin it around. And this is because of centripetal force. The centripetal force causes the movement of the water to go within this in the bucket itself and not fall out as it moves around. Bit of a random analogy. Let me know if you know what I mean in the comment section. But that it always comes to mind when I think of this topic for some reason. So you could be asked to discuss in a very simplified way the stability of orbits depending on the size of the path. And this is all due to gravitational forces of attraction. So I've got a scenario here. We've got 2 orbits. We've got the moon and the Earth, obviously, and the moon orbits around the Earth. The first one, part A, you can see that the orbit is quite small, the moon is quite close to the Earth, and in B, the orbit is larger and the moon is further away. So which scenario, A or B, does the moon, the satellite, travel fastest? Well, it's going to be A, and I'm going to discuss why that is. So you need to know that a stable orbit in a circular orbit motion, the radius must change if the speed changes. So this is due to gravitational forces of attraction, and they decrease as the distance increases. So if we look at B, you can see the moon is further away from the Earth, which means the forces of gravity acting on that satellite is weaker than what it would be in A because it's close together in A. So we know that the greater the force, the greater the gravitational force, the greater the acceleration, and therefore the greater the change in velocity, and therefore the satellite will move faster. So if we look at our orbital path, if we remember, if it's a circle, the radius, which is the line that you see that I've drawn, the white line that represents centripetal force, that is the radius from the center to the edge. If we have a smaller radius, essentially a smaller orbital path, we have more forces of attraction, and therefore you have an object that moves much, much faster around it. So, just in conclusion, this essentially means that orbits that travel faster, or objects that travel faster in an orbit, it's due to the size of that orbit. So, a smaller orbit itself will have a faster moving object, whereas a larger orbit will have a slower moving object. And we can actually see this in motion with the length of our days. If you think about the length of time it takes the Earth to move around the sun, we can see that that's 1 year. However, if we think about other planets which are further away, it takes them a lot longer in comparison to go all the way around the sun, and therefore that is why, because they're moving at a slower pace because the force of attraction is weaker. So in order to change orbital speed, the object must actually change the radius of the orbit at the same time. And this is to maintain a stable orbit. If everything changes too much too soon, this will become unstable. So that's essentially the key bit that you need to know. So there are different types of orbits. We have elliptical orbits. So these are ones that are oval shaped, and specifically this relates to comets, which are natural satellites, and they orbit stars. As the comet actually gets closer in that elliptical orbit, it actually increases with speed, and then it will slow down, and then it will increase with speed again and then slow down. Remember, this is all to do with the force of attraction of gravity, and like I said earlier in the previous slide. We have circular orbits, like I mentioned before. So this is the ones that we typically think of with the moon, which is a natural satellite. Also some other artificial satellites as well. And these are the ones that will orbit planets, specifically Earth. Specifically, those artificial satellites, we've got geostationary orbits, which are circular, and these are around the equator line. And this appears stationary to somebody because the relative speed is the same as the movement of Earth, and therefore it doesn't appear to be moving at all. So it looks stationary. However, it is actually moving just around the equator line. And we also have polar orbits, and this is for artificial satellites as well. So these orbit around the poles. Both of these are really used for things like climate, conservation, statistics, data, looking at weather patterns, that kind of thing, because it's close to the Earth and it's interested in like the world view, if you will. So looking at weather patterns, etc. Now you might be thinking to yourself, well, how do people get satellites out there? Because we as humans have actually put satellites out into space. How does that actually work? And again, it's all to do with the speed of those satellites themselves. And we're going to talk about this now. So here we go. Some students might be thinking, well, if you can put a satellite out into space, how do you make sure it doesn't fall back down again? Because if you put a satellite out into space, it could just fall back down, because surely the force of gravity is going to bring it back down to Earth. Or what happens if you put it too far out into space and it just wanders off to another larger massed celestial body that's attracting it? How do we make sure that the satellite stays where we want it to? So this is all to do with speed. So if we have an artificial satellite, and it's too fast, so around 11,200 meters per second, the satellite travels away into space as the attractive force of gravity is too weak to keep it in orbit. However, it's too slow, and this is less than 600 meters per second, the satellite will actually fall back to Earth and crash land as the attractive forces of gravity are too strong because it's too close. So this is kind of like a Goldilocks scenario where you have to get it just right. And essentially, we have to make sure that there is this middle ground. So we don't want the satellite to be moving too fast or too slow. We really need it to occur around 7,600 meters per second. And this gives it a nice stable orbit. And this will make sure that the satellite will move in a nice circular pattern around the Earth. Now, depending on the exam board that you're studying, will depend on whether you need to know this specific information in addition to whether you're a higher tier student or not. I would recommend just have a quick look at your exam board. I will link some resources where you can do that in the description box. But it's just worth knowing that in theory, you could have a satellite that would fall back down and a satellite that could go off into space. It just depends on its initial trajectory, and how fast it's moving will depend on whether it stays in a stable orbit or not. I hope you guys found that video helpful. If you did, feel free to give this video a thumbs up. Share this with someone else who is studying GCSE Physics. If you would like more GCSE content, feel free to give the video a thumbs up, share it with someone, and do subscribe. And thank you so much for your time today. I've been the GCSE Science teacher, and you have been curious. Take care, and I'll see you in the next one.